Hey, good morning. So I'm going to address a couple of student comments and then Friday quiz, and then we'll get into our discussion for today. So there were some comments on the website about there being some errors in the system. So I've reported those errors. Um, but for the most part, the system seems, I mean, there are some errors, but not, let me put it this way. Um, does not affect student scores. So there are some errors for the homework. Okay. And so I've uh, updated the scores in the homework. So if you don't see any updates in your homework, if you've lost any points, just send me an email and then I'll address it on my mind. And then several students send me an emails about the Friday quiz. So I'm going to go over the Friday quiz, just let you know, over the two problems. Yes. Today? Uh, yes, but let's hold off for a few minutes. So I'll just go over the Friday quiz and then we'll go over this one too. By the way, all the quiz solutions are being posted on the class notebook. So you should be able to check. If you look at the class notebook, you should be able to check in the section under quiz solutions. Also, you had asked about PDFs. I haven't gotten around to doing that, but I'm going to do it. It's on my to-do list. So I'll do it right after class. So it's there. Uh, let's bring up the class notebook. So let me bring up an empty spot right there. And okay. So if you go into the content library right there in the quizzes, you have the quiz solutions on there. Okay. So they're all on there. Mentioned this before, but just in case if you haven't yet taken a look. So I'll post the solutions right after class. That's, I'll get back to my office around 2:10, 2:15. And then before I leave for my, for the clean room, I'll post it in there. All right. So the Friday quiz. Friday quiz was about half-wave rectifier, right? So except for the last one, the first three were kind of straightforward. You had a capacitor, you had an equation for the capacitor, you plugged in the values. So let me just add a page. Let me write down Friday quiz number 5. Friday quiz 5. I think the first question was about the capacitor. So you simply plug the values and solve for the capacitor. Okay. V ripple VR was specified as a percentage of the DC, right? So we were given the output DC voltage was given, and then the current was given. So IDC, the output current was given. VR was specified as a percentage. So that means VR would be equal to VDC plus 5% of VDC. I think most every student got this one correct. So but that's what it meant, right? You have a ripple, you have your output voltage like this. This is your desired output voltage, and so your ripple is somewhere here, right? And so this value is 5% of VDC. That's what it means. 1.5%, sorry. No. Yes. Yeah. 1.5% of VDC. Oh, sorry. Thanks. I jumped ahead. And then VP, or the peak voltage required, would be VDC plus 5% or 1.5% of VDC, which is V ripple, plus the diode turn on voltage V on. Okay, our book uses 0.7, so we use 0.7. If it was 0.6, we use 0.6, you still get the right answer. Okay, so this would be V ripple because your peak voltage from the transformer must be larger than the desired voltage, right? Because some of it's going to drop across the diode. So you plug these values into your equation, and VP basically was the second question. And then I can't remember, what was the third one? Third one was IDC or IP, I believe. And again, that was also a standard equation. Now, the fourth one was the surge current, and I believe that's where the error might have been. Peak repetitive current, sorry, not the surge current. Should have printed it out. And this, I believe there was an error in this equation. So this is something that I've reported. Possible error. Instead of the half wave, I think the system had the equation for the full wave, and that's why it was giving incorrect answers. Yes. V1 was not given. 0.7, yes. Yeah. Okay. Were there any other questions? So yes. Yeah, for our book, yes. 0.7. No, it's inside. So this is the output from the transformer, right? And you plug a capacitor in there, it's going to charge discharge. So the ripple is right here. So the ripple is inside the peak voltage. This is the output of the transformer. And then when you place a capacitor in there, output from the transformer and plus the diode. So the output of the transformer, the input that is going into your power supply must be greater than the diode on voltage plus the ripple. Right? The output of the transformer is a fully rectified waveform. Then some portion of the transformer voltage will be dropped across the diode. For a half wave rectifier, it's one diode. For a full wave rectifier, it's two diodes. So whatever we do, whatever input we give to the system, to the power supply, it must be larger than the ripple plus the diode turn on voltage. So if you think backwards from the output side, which as an engineer, that's what you'll do. You have an output that's a desired output, and you need to go all the way back to the front, right? Moving backwards. So if your output is, let's say 10 volts is required, then you need to add the diode turn on voltage to the 10 volts. If you design a half wave rectifier, then 0.7 needs to be added on top. With a full wave rectifier, you need to add 1.4. Then if there's a ripple, you need to add that also on top of that. And then you work backwards. So your output DC voltage plus your diode turn on voltage plus your ripple should equal your transformer input. Transformer output into the system. Otherwise, your system, we wouldn't get 10 volts, right? There's only two down voltage after full wave bridge, right? So the full wave is just, there's only one. Yes, yeah, center tap. Okay, so that was the Friday quiz, and Monday quiz, I'll post the solutions later this afternoon. Okay, so where were we? Chapter 5, FET. JFET characteristics. Let's see. And I believe I mentioned this last class when I started it, before we began chapter 5, is the reason we do JFETs is because, our current material, it's been in existence for a while. When you get to semesters, material will change. JFET may or may not be carried over. Because by far the most popular ones are now MOSFETs for the last several decades. So we look at MOSFETs, and then we are doing just enough JFETs, so you're familiar with the device. So you perform the experiment lab 6, which is next week. And then after that, after today, not today, after Wednesday, we'll get into BJTs beginning Friday. That's the bulk of our material. All right, so in JFETs, we looked at channel resistance. I need to bring up, let's see, the equation for ID. Okay, equation for ID is IDSS times 1 minus VGS over VP. Okay, this is kind of like the diode equation. Okay, valid for most use cases. IDSS itself is part of the manufacturer's spec sheet and can be given by Kn over 2 times Vp square. Kn is a transconductance parameter that is again specified by the manufacturer. IDSS will be specified by the manufacturer. Okay, so it will be on the spec sheet itself. So to bias the JFET, we are going to apply a voltage between the drain and the source. We're going to use the same on the input side. So in this problem, IDSS and VP are given to us. IDSS is minus 5 milliamps. Peak voltage or VGS off is minus 5. It's an N-channel JFET. So the more negative voltage we apply at the gate, the more the channel becomes, and eventually past 5 volts, the channel will turn off. All right, so the question being asked is, what is the Q point due to this biasing condition? It asks for the Q point. It's asking for the value of the drain current ID, which the drain current ID is also mean it's IDS, because the current flows between the drain and the source. And then VDS, okay? So you're asked for ID, VDS, and of course, we can't calculate those without VGS, so we need to find VGS too, okay? So let's apply KVL to the input loop and determine what our VGS would be. So the input side, we have 3 voltages. We have the gate resistor RG, the source resistance RS, and then the voltage between the gate and the source, VGS. Okay, so we need to determine what that voltage is. So if you apply KVL, we get VRG plus VGS plus VRS equals to 0. Substitute those as a function of their currents, and we can write IG times RG plus VGS plus IS times RS is equal to 0. Typically, IG is going to be very, very small. One of the properties of a JFET is that it has very high input impedance or high input resistance. So gate current is almost close to 0, highly negligible. So if we assume IG equal to 0 or approximately equal to 0, and IS should be equal to the drain current ID. We can write VGS is equal to minus ISRS and also equal to minus IDRS. Okay. Steps are applying KVL. That's typically the first step in any biasing analysis. We apply KVL on the input side, KVL on the output side, and we generate our equations. On the input side, we have three voltages, voltage drop across RG, voltage drop across RS. Apply Ohm's law. That voltage drop is due to the gate current IG and the source current IS. Source current is the same as the drain current ID. Gate current IG is typically negligible. So if gate current IG is negligible, then the voltage drop across RG can be assumed to be zero. Very close to zero, but for purposes of analysis, we assume it to be zero. So we can write VGS is minus ID times RS. Now, we don't know what ID is, but we can determine by using this equation. So if we plug in values, I can write VGS is minus IDSS 1 minus VGS or VP whole square times RS. And RS is given to us as 1000. So we plug in these values and we solve for VGS. For VGS, you obtain as VGS square plus 15 VGS plus 25 is equal to 0. If you solve this, we obtain two values for VGS, minus 1.91, or VGS could be equal to minus 13.1 volt. Okay. Yes. No, IG is negligible because the JFET has very high input impedance. So IG is very, very close to 0. So purposes of analysis, we assume it to be 0. So once you have a quadratic equation, we solve it. We have two possible values, minus 1.9 volts, minus 13.1. If the JFET is on, what do you think is the value? Was 1 minus 1.91. 2 volts for 1.91. Anyone with 13? Right? Since VP is given as minus 5 volts, the most likely value for VGS would be minus 1.91 volts. So we can use that voltage. I'm going to go up here. And I can write, since ID is equal to IS, and determine VGS, not VGS, as 1.91 milliamp. Now you apply KVL at the output, or KVL for the output loop. The total supply voltage, VDD, is divided across three different voltages: VDS, VRS, and VRD. VDS plus ISRS plus IDRD. If I rearrange the terms and I solve for VDS, I can write 12 minus 0.00191. Saying ID and IS would be approximately the same value. RS plus RD is 2000 plus 1000 gives me 3000. Therefore, I can find VDS is equal to 6.27 volts. Yes. Which one? Yes. Yeah. That's when the channel would turn off, VGS off. That's the voltage that is required to turn off the JFET. The JFET channel is normally open when it goes to, when the gate source voltage goes to minus 5 volts, channel turns off without any application of input at the other end. All right, so Q point is the operating point of the device, meaning if you apply 12 volts at the output of the JFET, then the drain current would be 1.91 milliamps and the drain voltage would be 6.27 volts. Yes.
So always assume that the impedance at the gate is just extremely high.
Gate, yeah, that's one of the properties of JFET. So the question being asked is, should we assume that impedance is high? So there is no assumption for that. That's actually a fact. Now the assumption is, for the purposes of my analysis, if I want to make things as simple as possible, then I'll assume that gate current is completely zero. In real life, might be a few microamps. So in the lab, when you perform the experiment, we'll apply a voltage at the drain. We'll also apply a voltage at the gate, but it'll be a very small voltage with a very high resistance. Okay. All right. So we'll end class here today, and we'll pick up here on Wednesday. We'll begin MOS, device physics for the MOS transistors, and then on Friday we'll begin BJT. Okay. All right. So the homework for the JFETs, for the FETs, is not due until later this month, which is just a placeholder. So then I'll rearrange and I'll probably make it due like Thursday or so. Okay, so get started on that FET homework. Yes. Yeah, Canvas, that's more like a reminder, but the Connect homework is the main deadline. And Diego reminded me about it, so I moved that back.